Hopefully you remember some of your trig that you learned over the last few years. If you have a right angle triangle with an angle in it, if you're looking at the triangle from that angle, that's the opposite side, and this is the adjacent side, and then of course the hypotenuse is C. Pythagorean theorem, just because that is a relationship that holds in a right triangle. The definitions, what you might call the classical Greek definitions of trigonometry, are within a right angle triangle. Sine of that angle is A over C. Cosine of that angle is the adjacent over that, B over C, and tangent of that angle is A over B. So in other words, it's the opposite side over the hypotenuse. And I'm sure you remember all of this. And opposite over the adjacent side. This only works within a right triangle, and if you think about it, the biggest this angle can be and still have a right triangle there is 90 degrees. If you made this bigger than 90 degrees, you can't have a right triangle anymore. Right? If you try to draw a right triangle where one of the angles is bigger than 90 degrees, you don't have enough degrees left to make the other angles. It's not a right triangle, it's not a right angle over here anymore. So if we want to extend this, and that's what we're looking at in grade 12, is extending this to all the angles, any possible angle. So we have to define the trig functions a little bit differently, or extend the definition so that you're not just looking at angles from 0 to 90. If you draw an angle, in standard position that's less than 90, still you can make a triangle here and look at it in terms of the that side, and this side. But if we want to extend it, we have to kind of think about this a little bit here. This side over here is the y-coordinate of this point. And this side down here is the x-coordinate of that point for that triangle in there. So if this is theta. Now what happens here is that if we want to extend the definition so that you can look at angles over here or over here, you define the trig functions in terms of this, in terms of these coordinates, not in terms of opposite and adjacent and hypotenuse, because opposite and adjacent and hypotenuse, as soon as you flip it over to the other side, it doesn't work anymore. But if you define this, the sine of the angle as, if this is a unit circle, okay, a unit circle is a circle with a radius of 1. If you put a 1 there, the sine of this angle is y over 1. Or in other words, the sine is the y-coordinate. The y-coordinate of that point, if this is a unit circle, okay, so this is key here. If this is a unit circle, then the sine is the y-coordinate. And similarly here, if you define the cosine ratio as x over 1, if it's a unit circle, you can just ignore that 1 and you get cosine's the x-coordinate. So the unit circular definition of trig functions is this. The sine is the y-coordinate, the cosine's the x-coordinate, and then it allows us to rotate all the way around here. We'll go to something a little more dynamic here. So this is a unit circle. If you think about the angle as I rotate around here, no, not that. If we go around here, this is not sure why. Oh, I'm moving the wrong one. That's why. Those makes for good video. It's all good. As you rotate around here, let's get rid of the reference angle for a second. As you rotate around here, the values of each of the coordinates changes, right? As you change that triangle, what's happening with the opposite side here, this red one? It's getting bigger, right? Don't forget the radius of this thing is 1, so we can ignore that, right? The sine ratio of this angle in here is 0.98 over 1, or just 0.98. If it's a unit circle, as long as you think about a unit circle, you can ignore the opposite over hypotenuse, and you can just think about the opposite for the sine ratio. So let's look at that, and I think what I did is make it so it's, come on. Okay, so this vertical line here is going to kind of be a visual for what's happening with that sine ratio. Okay, this red line here is just going to show what's happening with the sine ratio as you go around here. For angles less than 90, you can just imagine this triangle, right? Because that angle is in that triangle. But as soon as you go past 90, right, the angle isn't in the triangle anymore. And you couldn't use the kind of the Greek definition, which is opposite over hypotenuse and all of that. So the circular definition of trig functions is looking at these coordinates right here. Okay? Looking at, well, not this one because it's not in the center. That's my other issue here, but I'll turn that off for a second. So, get rid of that. As you go around here, just let's watch the red one for a second. Okay, the red one starts, if you have an angle of 0, or a very small angle here, it starts at 0 and starts to increase, the sine ratio. What's the highest the sine ratio is going to go there? It's going to go to 1. Can't get higher than 1 because you can't have, this red line can't be longer than the hypotenuse, and the hypotenuse is 1, so that's the highest it can go. The highest the sine ratio goes is 1, goes up to 1, and then it starts to come back down again to 0 for the first 180. And then as you keep going, what's going to happen with that coordinate there? It's negative now. It's going down to -1. And then it comes back up to, my label doesn't show it as negative because it's showing it as a length. But it is negative, right? It's below. And as you keep going there, it comes back up. So the cycle as you go around, the sine is positive for quadrant 1, positive for quadrant 2. Comes back down to 0. It's negative for quadrant 3, and it's negative for quadrant 4. You learned that in grade 11 trig, actually, right? You learned a way of remembering where the different trig ratios were positive and where they were negative. You learned that sine was positive in 1 and 2. Like all of them are positive in quadrant 1. Sine is positive in quadrant 2. And then it's negative in those two. If you want to think about the graph, we're going to start looking at the graph eventually. I want to show you that now, but the graph of this is, if you graph the, come on, nothing but trouble with this today. If you draw the graph of this thing as you go here, this graph is going to show the sine ratio as the angle gets bigger. On the x-axis here is the angle. On the y-axis is the sine ratio for that as we go around here. Okay, so as this goes around, the sine ratio goes up to about 1, and then what starts, not about 1, it goes up to exactly 1, and then what starts to happen to it? Comes back down again here, right? So that comes back down to 0 at pi, halfway around, and then it's going to become negative, goes down, and not filling it in nicely, but, and then it's going to come back up to 0 again. What's going to happen if I keep going? After that, what happens? Yeah, it's going to repeat that pattern, right? That cycle there is going to just repeat. If we draw a graph of the trig ratios as you rotate around, it just goes up, it goes down, it goes up, it goes down, fluctuates between 1 and -1 there. This allows us to talk about trig ratios for more than just 0 to 90 degrees. We can talk about trig ratios for anything. The Greeks, I guess, designed trig ratios because they were working with problems within triangles. But we're going to apply trig ratios to anything for a number of degrees here. And when you have anything that rotates, you need to have angles that are more than 90. You need to be able to have any angle. So a lot of the applications we're going to do are going to deal with things rotating around a point like this, and we're going to represent them with trig functions. So if I keep going here, it's going to skip a few points, but it just keeps repeating that pattern. Okay. If I went the other way too, if I went to negative angles over here, it's going to just keep repeating that pattern. All right. Now similarly, if you look at the cosine ratio, so we'll get rid of that. We will look at the cosine ratio here. Actually, I should stop this before we look at